So it's kind of odd, but it's good to be here, and it's fun. It's really fun to be in front of all of you. This is such a great topic. It's all these. I keep thinking, David's talk. That was fantastic. I really enjoyed it. I've been I missed Jennifer Tessie's talk yesterday, and she's hopefully I'll be meeting her today. I've been working with her off and on for years about culture and the kind of the sociology of engineering, which is a lot of fun. And this is what this talk's a little bit about. And this talks a little bit about how I think failure really does help us define us. Now, it has mixed blessings because sometimes we overreact when things go bad. You know, we find a problem, we make new rules, new shall statements. You've heard of those. That just ends up burning it. And the people then you have to, if those rules don't make sense to the application you're working on, you have to justify your actions, why you're going off road, what everyone told you to do, because that last failure was such a big deal, and institutions all worried about it. So this is it's a mixed bag, but I have to admit, I learned from many of these people who helped develop the space age, who were starting work in this business before the space age in the 40s and 50s, and they were able to tell me about how the transition into the space age came about, and being around JPL since about 1980, I was able to watch and be part of some of the evolutionary steps that got us here, including how. So maybe next year I'll come back and tell stories about the history of avionics and software at JPL, at least for deep space. I mean, I can't speak for everybody, of course, but at least at JPL, about how we started with, what's inside Voyager. You might be surprised. Did you know that Voyager has self-modifying code? Cool. Yeah. How many of you do that? Right? Have code that writes on top of code. You do. Oh, good for you. Patching. Well, yeah, but real time, automatically, and every day, all the time. Yeah. Yeah. No boots. You just do it. No rebooting. You just like, oh God. And this is what happens when you have enough memory, right? And you have plated wire memory, which, by the way, more reliable than flash in space. Just saying, Anyway, let me get to my story because I have a lot of words. So let's see if I can make this thing work. So you guys know the story about the W40? Yeah, you've probably seen this before, right? This is probably boring for most of you. So about 60 years ago, some employees of American Rock Company, chemical company, wanted to develop a product that would prevent rust. And they were trying to get into the aerospace industry. And they were very methodical, and they took careful records. And so they labeled their first effort water displacement test or formula number 1. So how many times did they fail before they were finally successful? Yeah, they failed 39 times. 40th was the winner. And so this is actually true. It's a true story. I mean, but it's probably about. So I'm really talking about the story of iteration, about giving yourself spaces to fail. All of you are, have been developers, and they know how important it is to sandbox and develop your stuff privately. I mean, it's nothing more embarrassing to have your code execute for the first time on $1 billion mission. That'd be kind of tough, huh? Yeah, it's happened. So I often ask our staff questions. Have you experienced failure? It turns out that not everybody has. That's really boggles my mind. And they asked him, I says, well, it was a bad experience. I mean, he was, oh yeah, terrible. Are you afraid of being wrong or making a mistake? And I said, and they say, well, yeah. Some say, no, I've been down that road before. I've broken stuff before, and I've lived to tell the tale. So, and so the question I have is are we ever good enough in our jobs to be able to say we don't make a mistake? And I'd say failures are what humans do, and engineers are no different than any other humans. Well, I mean, a little bit different. But if anyone fails, how is it possible that we can land complex, $1 billion some plus missions, your code, on other planets? Well, it turns out there is no secret, because all of you really do know the secret already. This crew in particular. We have, first of all, at JPL, we do have the luxury of hiring very smart and diverse people from all corners of the globe, and that's a real plus. Having people who are intelligent, enthusiastic, um, who they're driven by an innovative spirit. Um, many of you, in fact, you do flight software, so therefore you're not going to get terribly rich, are you? um, I mean, we could all go. Many of us could go work for companies and maybe make quite a bit more money, but we wouldn't be necessarily as inspired or motivated to come to work every day that like most of you are. And we have a belief at JPL. Goes way back. Is technical authenticity. I love that term. What it really means is that we celebrate people who know for real and not third or fourth hand. Or they. I heard from Sarah who was told by Joe that, but no, it because you read and looked it up, understood it, and it made sense to you, or you could see it for your own eyes. That's a technical authenticity, and there's something very powerful that. And if you have a culture in your environment, your organization of celebrating that and recognizing that among your peers, you're halfway there. We have at JPL going because JPL was owned by this place and run by this place and was started by this place. It's actually a university lab run amok. I don't think any of the university lab has become as crazy as this place, as JPL, that place, I should say. But so it started. So as a laboratory, it grew up in the culture of an academic institution where you were encouraged to say what you thought. Isn't that great? To say what you thought without being people might just groan or yell at you, and there was a time that people were not so elegant on how they did that. And what's more, people, because of this belief in technical authenticity, people believed it was okay. I mean, if you were the boss, if you're the chief engineer at JPL, or somebody looked at you and said, "Talk to me," they wouldn't treat me because talk to me as if I was the chief. They would talk to me because I'm Rob, and because I had these experiences or didn't have the experience. And so people would say, "Rob, you're wrong." I love when people do that. I mean, and so that sense or you have to earn your stature. It has to be authentic, and people have to believe that you either want or want to understand, and are basically built um, uh, toward belief in that something someone else doesn't. That I'm sorry, I'm going off the rails here, but that other people know something that you don't know, and you're being looked at by your employees as being somebody who's actually earned their keep and actually who knows what they speak about. So that's something goes way back, and that's certainly true at Caltech. I tell you, thinking systematically. That means when you see something odd, you often have to ask yourself, why is it? If it's odd here, why wouldn't it be odd over here? Why wouldn't this be more systematic? And we do that a lot. It's very tedious to think systematically, and of course, being humble, which we're actually not terribly good at, but we believe in it. Um, um, and a willingness to lay bare our shortcomings, and to be honest, and to work and sharp our weaknesses. I think those are very important features which we often don't have time to do and we don't talk about enough. And also acknowledging curating our strengths. When we're good at something, let's stay good at it. We have one of the worst things that happens in most organizations is some of the finest technical engineers go off and become cost and schedule managers. It's great, but think about the incredible experience that you're losing when that happens. Of course, another one which is just goes with all the work we do is it takes work. It takes hard work. It takes perseverance. It takes keeping at it to make something happen. So let's talk a little about some stories from real man. So the Ranger program was a program of multiple spacecraft that were supposed to go to different sites, and they were aimed for the moon. Now nothing had been no human-made object had actually gone to the moon at this time, and certainly this wasn't supposed to really land on that moon. It was supposed to kind of crash land, And as it came closer to the moon, it would take pictures, click, 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 click. And it had this little balsa wood thing with a rocket on it. See that little, the big ball on top? That was balsa wood, and it had a seismometer in it. And it had a solid rocket motor attached to it that would launch off just in seconds before impact, cancel the horizontal velocity because it was spin stabilized, and then crash land on the moon, and then self-right itself and transmit seismic data back to Earth. Okay, well, what happened? So as it got closer, it's supposed to get like 1 pixel, 1 meter per pixel, which is pretty good. This is a lead into the Apollo program, right? And so this whole idea that was that we were supposed to do it, but I get it working, but it didn't actually work as planned. So the first one had 2 problems. First, it was on the launch pad, ready to launch, and all of a sudden, due to a high voltage event discharge, all the solar panels and the antenna all deployed inside the fairing. It's like a cartoon, isn't it? Yeah. I've seen movies where that happened. And then a month later, we launched it, and the upper stage oxidizer manifold, which was controlled by the spacecraft actually, failed to make contact to emit fuel to engine so the engine never burned, so it never got into orbit. And then another launch failure, and the next time around was traced to a failed gyro, which never explained, by the way, why it broke. And then the upper stage, the Atlas, the radio launch guidance failed, and the spacecraft guidance had a sign error and missed the moon by 36,000 miles or kilometers. I'm sorry, long ways off. So Ranger 4, we're getting better, right? Getting closer. The main timer in the spacecraft computer stopped in that case, and so there was no deployments and an impact to the moon on the far side. Nothing. So far, not so good. 0 for 4. Now 0 for 5. Electrical short in the solar panels failed and missed the moon by 450 miles. I could get to miles, but units. The original Ranger, actually, ironically, the original Ranger 5 was pulling off the assembly line and remodified to become one of the Mera spacecraft, which were actually successful, the first one to fly by Venus. So we had the failure review board, and they said JPL's pattern of shoot and hope really wasn't working, and it wasn't conducive to success. So we finally got so the JPL did a whole bunch of changes, and I'll talk about that. The spacecraft redesigned. They got rid of the balsa wood lander, and then they did another one, and that failed too. It worked perfectly, actually, hit the moon, but guess what? It took all the pictures while it was being launched. The reason is that there was an umbilical sticking out in the breeze, and it shorted out the wires as a test wire, which caused the hardware timer to click off to take the pictures. So that didn't work out. So Ranger 7 finally came along, it hit the moon. We got pictures. Ranger 8 did the same thing. Ranger 9 did the same time. Now, this is a good time to quit, wouldn't you say? Okay, but think it was 9. So you get 3 successes for 9 attempts. Whew. That was really bad. So JPL really changed after that in the early 60s. JPL was completely reorganized because it was a university laboratory, still model. That was how it was operated. It really wasn't, aligned with product development, and so things that were informal became more official. We wrote things down. The new emphasis was placed on line order responsibility. So there was an organization called software. For example, there was an organization for avionics, guidance control was one system, command and data handling was another system, subsystem, for example. System engineering that spanned womb to tomb, that went through the whole architecture. David's talk, he's really a system engineer, wouldn't you say? He's not just someone who's coding the design, the inner loops. He's actually seeing the whole thing through, stem to stern. That's a system engineer. We didn't have those before. Many technical lessons learned about isolation, the idea of fault containment. We stopped cooking our spacecraft. We actually were trying to kill the bugs. So we didn't want to bring Earth bugs to Mars. So we cooked our spacecraft at 200 degrees Celsius for a couple of days. Then we launched it. What do you think? Did that work? Anyway, no one has a clue whether that worked or not. So we learned out it's better to scrub out the design details and manufacturing defects before you launch it. Okay, that was a big deal. So JPL really changed a lot in the early 60s. And then Galileo came along, which was intended to launch in 82. I'm skipping Voyager, which was remarkable successes, though it had some really cool failure modes. I did mention that was self-modifying code, didn't I? Yeah. Um, Galileo was a really complicated mission. And we were one of the challenges of this mission. I won't even go into those details, but they had this deployable antenna that looked a lot like the TDRS antenna in orbit around Earth. That's used for as a communication relay. Um, this antenna was installed and closed before its intended launch in late 1985. However, the Challenger disaster slipped the shuttle launch, which was supposed to launch on, to 1989. So the antenna was not unfurled again until a year after launch, when we were trying to we opened it up as it was spinning around the sun, getting enough speed to get to Jupiter. So it got stuck closed, and we cannot get it unstuck. So the cause, well, perhaps due to the vibration of doing its 3 cross-country truck trips from California and Florida, the dry lubrication between the ribs and the hard points at the top wore away. That's has been our hypothesis, and it makes sense because we tried to reproduce it, and we did. The antenna lubricant was not checked or replaced before launch. The power switch used to run the actuator motor in both directions had been repurposed to only go open, it couldn't close. So we couldn't, lighten the load and get some metal working to get it open again. We used that. We didn't have enough switches, so we used a spare switch for something else. But what happened? So now you're stuck with no antenna. You're headed to Jupiter, and your big antenna isn't working. You can't communicate with Earth. What do? What you do is that you use your low gain antenna. Well, what's the data rate? You're lucky to get 10 bits per second. 10 bits per second. Have you actually tried to watch a spacecraft or anything at 10 bits per second? But it's better just to let the data collect, go out and get some coffee, and come back in a few hours, see what you might get. It's not very conducive for getting lots of high resolution imagery. So we had to redesign the spacecraft. We used the attitude control computer to do image compression, and among other things. And so we also had to array antennas in the Deep Space Network, so that in order to up the signal gain, to get the higher 100 to 200 bits per second, we had to have multiple stations listening to the signal at the same time, perfectly in sync, time correlated. So recorded open loop RF, open loop recording, brought all the tapes back to a machine tape recorder that unwound them and add the signals together, so we can actually detect bits. That's how we. And so Galileo didn't do what it was intended to, but over the course of years in orbit, it actually did pretty darn good. We discovered that lossy data compression was actually okay with scientists. Now, there was a time that no scientist would ever allow even lossless compression, because they didn't like people mucking with their bits, right? You remember that? Oh, yeah. It's like, whoa, what are you doing to my bits? I don't trust those compressors. But they discovered not only is lossy okay, but a lossless okay, but lossy compression is actually really good too. And you could do things, and you can put on board your vehicle things to actually help you see the data better and get more data down. So we edited imagery, for example, with Galileo, when it took pictures of images of moons of Jupiter or of Jupiter itself, it didn't send any pixels of the black background of space. It basically cut it out and only sent the middle part. And also JPL really didn't like programming in assembly language. Do you guys like programming in assembly language? Isn't that fun? Yeah, you do. You like it. Good for you. Yeah. I have a nice old 1802 microprocessor you will love. The RCA. That's right. We demanded better computing. We realized that data system architectures that were flexible could really come in handy. You need to be able to. Sometimes you need to repurpose machines. But in fact, we added rules at JPL that says that you're supposed to launch with 10 to 20% an unallocated margin in your code. Now, why would we do that? Well, because of Galileo. So Galileo, we realized we often had to repurpose our machines for around failures. We didn't have redundancy for that antenna. The redundant thing on Galileo was a big old tape recorder, a reel-to-reel tape recorder. And I mean, I'll tell you, it's just like it sounds. You collect data real time instead of sitting it down out the radio. You send it right to the tape recorder. The tape recorder's collecting the ones and zeros, and when you're done with that, you play the tape backwards and you send the same bits you collected in reverse order back to Earth, and hopefully you can figure out which bit goes where. Um, we learned a lot from Galileo. It was a good experience for us. We did a lot of work to refactor our thinking about how spacecraft and systems should work. And then we have another spacecraft which is built on both Voyager. And look at this spacecraft. You'll see that big white antenna there. If that antenna looks like the Voyager antenna, well, you would be right, because the Voyager spacecraft, we had a third flight antenna that we bolted on top of this box, and we put the Galileo electronics inside. So this was a kind of a Frankenstein of spacecraft that was sent, or that antenna was being used not just to communicate back to Earth, but also used as a radar antenna to bounce signals off of the surface of Jupiter. So it's a mission. So we was intended to map the internal surface, the surface of Venus. And in fact, if you know, we had a global digital elevation map of Venus before we really had a high quality digital elevation map of the land masses of Earth. Isn't that wild? In fact, it was Venus. It was this mission that inspired Congress and others to fly high-powered synthetic aperture radar in Earth orbit on the space shuttle and other places. So, because people, how does that map compare with Earth's? Well, we don't have one Earth yet. We're working on it. So this was a very powerful, wonderful mission. However, it used the same attitude control computer as we use in Galileo, which was a bit sliced CISC machine coded in HAL-S. How many of you remember HAL-S? Do you remember HAL-S? Yeah. What'd you think of it? It's called HAL-S. Was the same software that was used in the space shuttle. Galileo flew it on the guidance control computer only. It was a predecessor for Ada. If you remember, Ada. The only difference between the two is Ada was the committee that designed Ada was vastly larger. And so Ada looks like something designed by committee, and it was. HAL-S was actually a pretty nice little multi-processing language. It had intertask communication. It had all the functions for equivalents of rendezvous or interprocess communication and atomicity. A wonderful system. But there's a different, for Magellan, the software team that was developing the guidance control computer was a different team than developed the Galileo machine. And one of the things it had was we discovered not long after we got into orbit around Venus, suddenly, and by the way, the vehicle at the time was sort of spin stabilized, moving very slowly. The attitude control system crashed. Software crashed. It was on a separate computer. It wasn't all integrated like we do today. And multiple times in a row. And so after multiple autonomous attempts, the central data system, which was separate from the attitude control system, decided that the attitude control system had enough of those resets, and so it decided to swap to the backup computer, and it did. But the same thing happened there, a bunch of times. I think that it's something order of 10 resets in a row. It finally gives up and swaps computers. But then you had the same 10 resets on the other computer. Huh. So what happened? Well, this happened several times, going back and forth, boing, 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 boing. At one point, the command data substance says, I need a dead ending strategy. The dead ending strategy was, if this happens over and over, it's probably not the computer over there. It's probably me. So the command data system would just let it be and just let the guidance control computer do its job of controlling the vehicle. When I say crash, I mean it's like goes off in Never Land and executes garbage. It is not processing at all. And so the computer was just about to give up, almost giving up. And I think I can't remember the numbers. I need to look it up. Something like 10. I think the dead end was after 10 or 12 attempts. and it made it almost to the last attempt before suddenly one of the two computers hooked and got it worked and kept working. Huh? Whoa! This had not happened before. Now, had this happened, uh, and had the computers had the computer not recovered at the last minute, we might have well been permanently lost, and the spacecraft would have been tumbling indefinitely around orbit on Venus. We would never have gotten that map of Jupiter, and who knows how long it would have been before people would have paid for radar tomography of the planet of our planet. So, what was supposed to happen? Well, the only asynchronous hardware interrupt, asynchronous, was from the star scanner into the attitude control computer. And when that happened, the star crossing event would come from a pair of slits from the star scanner. As the vehicle as stars crossed through the slits, as the thing was rotating, you get an interrupt. That's pretty cool. It's pretty simple. When this happens, the computer automatically disables interrupts, saves. This is the interrupt service routine handler. Disables interrupts, saves the current program counter on the stack, as you guys all know this, and starts the interrupt handler code, which quickly notes and logs the time and magnitude of the star for later processing before re-enabling interrupts and performing a return from interrupt. This is just, you've seen this a million times, right? Yeah. The whole idea is that another star crossing could happen at any time, because no one's controlling it. There's all sorts of stars in the sky. Who knows what attitude you're in? You can't control where the stars are. So, so it took years to figure out what happened. And JPL's Ted Koff, you remember Ted? You didn't know? Oh, yeah, not too bad. He's now retired, unfortunately, but he actually developed the multitasking operating system for the HAL-S used on the attitude control computer. It took him years to figure it out. It turns out the return from interrupt is the last instruction the interrupt handler. This is now assembly language stuff, right? The attitude control hardware, the flight computer, ensures that the new interrupt processing will not happen until the completion execution of the next instruction, which should be the return from interrupts. So you re-enable interrupts, then you return from interrupts. You've seen that before. However, there was one little instruction, assembly level instruction between the enable interrupts and the return from interrupts. And what happens if a star shows up there? Well, actually, even if one happened before that, if you have interrupt pending, suddenly you get another interrupt while you're still in the previous interrupt service routine. You basically get nested interrupts, and so you can guess what happened. That basically the timing of star crossings was consistent. It doesn't take that long before if each computer sees the same star scanner and sees the same star spacing between two stars, and those spacing have to be right there to sit in between this very narrow window of vulnerability, boom, you crash. And that's what happened. And if it wasn't for the fact that the vehicle slightly drifted and between restarts of the attitude control computer, we would have lost the spacecraft. So we learned how to be much more careful. We had one of the challenges of having your hardware team over here and the software team over here, and they don't talk to each other that much. You end up with problems. So we want to keep them close because those conversations need to take place. I'm sure you've all seen this before. Another problem mission, which is very famous. I'm sure you've heard of this. Certainly, if you have kids, they've heard of it because their third grade teacher told them about this. Was this Mars Climate Orbiter, and so in the fall of 1999, Mars Climate Orbiter was on its way to Mars. So the planned approach was that it would come in streaking past Mars. As it got really close, gravity would pull it in, and it would just if it didn't do anything, it would just change its orbit direction, but just scream on by. Instead, it has to fire its engines in that orange spot you see there. It would fire its engines to help capture it into an elliptical orbit around Mars. And so we were aiming for a spot in space that would actually call the B-plane target, but that actually allowed for that when gravity pulls you to the right spot, you'd be above the atmosphere, and you'd be able to fire engines backwards to slow down, retro firing, and then put yourself into orbit around Mars. Um, so that's the plan. Well, first of all, you do flight software, so all of you are rocket scientists, right? Yeah, I thought so. So look at this spacecraft. What does solar pressure do to this asymmetric vehicle? Torque. Yeah, this is a weather vane. Solar pressure, photons bouncing into that solar panel causes the vehicle to want to spin onto one side. Well, that if you're a spacecraft builder, you know that happens. That's going to happen. So you just have to deal with it. It's not a big deal. But what happened as we got? It turned out, unbeknownst to us, the vehicle had been moving to the left as it approached from the lower right, and was on a trajectory that was about 70 kilometers to the left, closer to Mars. So when it fired its engines, it was still above the atmosphere of Mars, but by the time it was done firing the engines, it had become a lander. Yeah. So this vehicle had basically, we had steered it into Mars by accident, and this orbiter burned up and tore itself apart on the surface of Mars. This actually happened. So Mars Climate Orbiter enters the atmosphere. Maybe actually 100, it was closer to 100 kilometers off course by the time it actually got there. 100 kilometers, that's a long way off course. That's a long ways. I know it's trying to get close, but so what do you suppose happened? Well, it took less than a day for us to realize that there was a factor of 4.45 underestimation of the thruster forces. So let's go back to that spacecraft with the solar panels off to one side. How do you correct for the torque? Well, there are two things. One, you have a reaction wheel, so you can spin up to counter that torque, but those reaction wheels saturate pretty quickly. You have to desaturate, means you have to slow them down again. But when you do that, to keep the vehicle spinning in the other direction, is that you have to fire thrusters. And if those thrusters are aligned on the vehicle to produce torque, but if they're not aligned, so the center of force goes through the center of mass of the vehicle, it would also cause the vehicle to move to the left. And that's exactly what happened. The vehicle kept moving to the left. But we knew that was a possibility, so we accounted for that by having the spacecraft report to us exactly what thruster firings it was doing. And the navigators were getting that information back to us, back to JPL, and to the JPL navigators. And that information was supposed to be in SI units. Now you recognize the 4.45? That's the difference between a pound force and a Newton factor. There are 4.45 newtons per pound. And the navigation was expecting to get this stuff in SI. Instead, we were getting it in pounds force. So we were underestimating the forces by a factor of 4.45. So we underestimated how to move it to the left. You say, well, that was the root cause, right? Well, that was the root cause. However, it was really the proximate cause. The root cause was three things. One is we'd seen weird things happen with that thruster, and the people who were being told that some weird things in the navigation data that they couldn't explain felt that was small potatoes compared to other problems with the spacecraft. So there were a lot of distractions, misunderstandings, and people who were seeing the problems weren't speaking up loudly enough. And there was no venue or plan. This is the most important. We didn't actually test those thrusters this whole process was valid. I mean, this could be anything. Yes, it's a units conversion error is probably the most embarrassing thing, because that's something that you learn as a kid. So we did learn a lot. Today we learned that we should test our thrusters. We should certainly learn how to do a better job of speaking up when things feel uncomfortable or off. But also, you might be surprised as how come we didn't know why was it why were we counting on a mathematical process to figure out where the spacecraft was, rather than just measuring the spacecraft directly. How do you measure your spacecraft? How do you know where your spacecraft is in outer space? You guys all know how to do that? Yeah. So the way you figure out where your spacecraft is, there's two tricks. It goes back for many decades, where you send a radio signal from the Deep Space Network or from a radio to the spacecraft from Earth, and then you have a radio that's designed to bounce the signal back almost immediately, like a mirror. So then you can time the return pulse that you get back. So boop, beep, bounces off the spacecraft, boop, comes back, and you time the boops, and there they are. Now you know how far away the spacecraft is. You still don't know where it's out there, still out there somewhere, but you know how far away is. You know the range. You can actually get speed too by sending a tone. Send a tone out to the spacecraft. It, the same radio mirrors the tone back, echoes it back at a different frequency, but it turns out, and it comes out, if the pitch changes pitch. If it's higher than you expect, it's coming toward you. If it's lower than you expect, it's going away from you. So now you know the velocity, but you still don't know where it is out there. And that was the problem. We knew exactly where our spacecraft is from the distance perspective, to within hundreds of meters, but we didn't know where it was this way, and it had been moving to the left the whole time. Mars was there, and it was approaching this from the right, and off it was go. We got closer and closer, and we didn't know that. Now we have a way of measuring it, because now we can triangulate our spacecraft with quasars. Isn't that cool? So now we can measure a quasar over here, quasar over there in our spacecraft, and we can beat the wavelengths from those two sources and from the radios. And now we can say, hey, it's right there. And so that was all something that we standardized. We knew about that technique before this problem, but we standardized that process from here on out. And then we had another problem. And 2 months later, you got to imagine this. Can you imagine if you worked for years on this project and also to have it crash into another planet? How do you feel about that? I mean, you worked years on it, worked long hours, weekends. There were people who were very upset, as you can imagine, very rightly so. They worked really hard, but we're humans. Things like that happen. And when things go wrong, it's not one person's mistake. It's all of our mistakes, because we're not seeing something. We didn't see the whole picture. It's usually multiple things that went wrong. About 2 months later, Mars Polar Lander on its probes arrived and vanished without a trace. What was it called? We never really figured out. Actually, we do. I think we have figured out. And I'll tell you. But there was no telemetry during entry descent landing. There's no way to. The spacecraft was designed to be quiet during entry to save money, because we didn't want to spend money on radios to communicate with Earth while landing. Now, some of you maybe see me on the web or something during landing, and I'm looking actually with a group, often looking at the signal coming back in real time. And we have multiple ways of doing that, either a direct to Earth link or a relay link via a UHF path to an orbiting spacecraft that we time to be overhead at the time of landing, that allows us to communicate back to Earth while the thing is landing. Very, very convenient. Mars Polar Lander was the first was the first Mars mission that didn't do that, and it happened to turn its radio off before entering, and the whole idea was going to land and then turn its radio on once it got to the surface, and we'd be able to hear from it. So we were in the control room this is December 3rd, 1999, just a few months after this vehicle crashed into Mars, and we're sitting there. Okay, we're looking at there's a spectrum analyzer, effectively a display of a spectrum, and we're looking at the clock, and there's a countdown clock. 5. We're going to get the signal. It's landed on Mars. Everything should be fine. 5, 4, 3, 2, 1. Nothing. We saw nothing. Now, a lot of people say, oh, don't worry, we'll just wait a little bit longer. Well, I'd worked on Mars Pathfinder. I happen to remember, I was the chief engineer for Mars Pathfinder, and I remember that every time the signal didn't show up on schedule, the software is rarely like minutes late. It's either going to be there on time or isn't there at all. And so I got immediately nauseous. I was looking through a glass window. The ops team was just a few feet away from me. Control room. I'm just going like, so I just, because I feel like I'm going to throw up. So I leave the building, and I was feeling, it was pretty bad. And and the team looked and looked and looked, and they never got any signals. What's more, there were two microprobes that were let loose just before landing from the vehicle uh, that were supposed to communicate via relays. We never heard from those either. So we left. So we had suspects at first. The leading cause was considered to be a spurious software error. You may have heard about this, where basically a software monitor had been enabled before the legs were deployed to look for touchdown. Well, it turns out the deployment mechanism actually causes the Hall effect sensors to trigger, and well, and we believe it probably did trigger that software, but the software monitor isn't pulled until it's 40 meters above the ground. So when you're about 40 meters above the ground, the main software goes, okay, hey monitor, look for those legs coming out. There should be leg detection, touchdown detection any minute now. We're landed. We landed a while back. Oh, okay, chop the engine. So that was the nominal cost for many years. We later on found out that probably wasn't happened because it didn't get that far. Because we found a bunch of new failure modes, and one in particular, we were pretty confident and we have to write a paper on this. We're pretty confident that the separation connectors, the cables that connected the cruise stage to the main entry vehicle, never came loose because they were deployed too cold for the mechanism to work. So at those temperatures, the mechanism would not work. So the cables would stay attached. The cruise stage would be free, but the cables would still hold it in position. And that doesn't work very well when you land. Entry does not work well with a cruise stage attached. And so the vehicle probably tumbled. Now, another reason we might think that, because we've taken 52 terabytes of image data, at least so far, of that area of Mars. And we've even given it to algorithms to search for parachutes and back shells and landers, and we've not found them. Though I have to say, we did find hundreds of back shells on Mars. That's on the part of Mars. Back shells. That's the back shell cone of the back where the parachute attaches. It's quite large, but the ones on Mars are about 10 times bigger. They're all natural. So we found so. We've never found it. And so this sort of explains what happened. But so a lot of things were missed. And I said, we learned the cruise stage never came off, probably broke up during Mars entry. So learning from Mars Polar Lander, we learned it's really important to find out what's going on. So I asked a question. If you were designing a system, and we were talking about keeping things simple, if you're trying to things you don't need, what don't you need to land on Mars? Communication with Earth. You don't need to talk to Earth when you're landing. It's just all open loop stuff. This is autonomous software. There is no need for you to add the complexity of radios and software to send bits and waste valuable CPU time on a Rad 6K with sending bits down to Earth while you're controlling the X-band when on the way down, or UHF or anything. You don't need it. But who does need it? Well, the next person who's trying to make another vehicle, they're going to need it. If it doesn't work, how would you know what happened? How would you be able to redesign your vehicle? How would you be able to argue that you can do it again? Remember what Ranger, ship and shoot thing, where you ship and hope. You can't do that at Mars. The U.S. taxpayers paying for this stuff. They're going to well, what makes you think it's going to work a second time? I don't know. Well, it turns out we were building a second lander that was going to do very similar kinds of missions at different parts of Mars. That got canceled. It was called MSP-01, Mars Surveyor Program number 1 lander, 01 lander. Well, it was put under plastic, and for years it was just stayed under plastic in Denver. And finally, we took the plastic off, refactored it, redesigned it, and tested the living daylights out of it. We launched it as Phoenix. Remember the Phoenix lander? That was Mars Polar Lander refactored. So we did, as a part of the failures, we also looked at all these different ways of landing safely. One of the things we came up with almost immediately was, for example, things like Skycrane, where you land a rover in such a silly way, lowering it down on ropes. Who in their mind would do such a thing, Eddie? Yeah, yeah, software. I, I thought you. I thought you. Oh, okay. No, no. I'm actually one of the guilty parties there. But no. So sometimes failure forces you to rethink things and refactor things, and especially if you're not sure what happened. Another kinds of failures. One of my favorite is my failures of our imagination. You recognize this? This is a wheel from Curiosity. If you see holes there, it's not your imagination. There are holes on our lander, on our wheels. Quite a few of them, actually. And this is actually, for me personally, very embarrassing. I was the chief engineer for Curiosity rover, and I knew that the wheels could crack well before we launched. Now, all of us who saw the cracks in our test vehicle, we talked ourselves into believing that that was a art test artifact, that we had over tested the test wheels by mistake and we broke them. Um, and it turned out we were wrong. It was, in fact, it wasn't a test artifact, and that we were mistesting our idea of how to test these wheels in a proper manner was ill-conceived. And we just, first of all, one of the things is, first of all, check this out. You're going to a place you've never been to. You can't see in the scale of sub meter on Mars at resolution, so you can't see rocks. But guess what? You're going to a place where you hope that there used to be water, like an ancient lake bed. Well, what's an ancient lake bed? It's clay. Okay, that's fine. Clay. We can drive on clay. Well, what about rocks? What if this Mars has meteorite impacts causing charged bits of rock flying everywhere over millions of years? Because this clay, if there's water there, was laid down 3.5 billion years ago. That's a long time ago. And there's plenty of time for other rocks to accumulate. And if there's any bit of moisture in between that causes the water to flow again, those rocks are going to get embedded into clay. And when you embed rocks on the surface of Mars over millions of years, what happens to the rock? Well, the rocks get sharpened by wind. The Mars only has 10%, I'm sorry, 1% the density of Earth's atmosphere, 1%, all CO2, mostly CO2. And what happens? Those rocks are stuck there. They get worn due to saltation, little bits of clays and rocks bouncing over the surface, grounding the edges flat. And we never thought about that. We didn't, in our testing of our wheels, we never glued the rocks down. We kept them we just put them on the ground and drove over them. When a wheel goes over the rock just bends over, and the sharp point doesn't stay fixed. It doesn't tear at the wheel. The other thing we didn't do is all three wheels in a row, because these rovers had three wheels on one side, three wheels on the other. They all turned exactly at the same speed. Now there's a problem there because of these wheels, which can move up and down on this rocker bogie architecture, the same architecture we started with Sojourner rover years back in the 90s. And so when these wheels go over, they have to a wheel has to go over a rock. It has further distance to travel. Yet if these wheels are moving at this speed and this wheel is moving at the same speed, this middle wheel is not going to move fast enough. And what's going to do is that rock is going to tear the wheel. And these wheels are made of aluminum. They're very, very thin because they have to be lightweight to handle the deployment conditions and launch mass. And so we failed to test three wheels in a row moving at the same speed. And we fixed that. We did. We went. We changed the software to on board. It's great. We modified the software to use torque control rather than speed control. At least more torque, and that actually helped a lot. We failed to imagine these rocks. We failed to properly test it, and yet all the data was there for us to see that this was a problem. So we did not put the pieces together in our heads in advance. But so we did fix it, and we fixed it again for Perseverance rover. We also made the wheels a little bit sturdier. There are better ways to fail than on national television? Yeah, there are better ways. I think safe venues where trials and lots of errors can happen without severe consequences and ridicule is very important. And all of you understand that as developers. You already know that story. But a lot of people don't realize just how important it is to give yourself time to learn and mull, committing to something new, because oftentimes we're in a hurry. The budgets are getting tighter all the time. We need to be able to talk to experts to sound out our ideas. We need to build models, try things out, simulations, prototypes to see how these things work. Share what you learn with experts and have people criticize your work. That's really important. Peer reviews, I think, are still something that are so essential. You can only go so far with lint-like tools. You need to be able to have people helping you think. Share the design with others. Invest more in high fidelity versions. The design, create independent testers look at your final design. Work your way up to the final design, and give yourself that time and space to do that. And monitor what you build, and check and look for bugs. And don't just throw it over the fence and hand it to someone else and walk away. You've got to stay with it. And we're trying to encourage our engineers who are responsible for the technical products to, even though they may be officially done with delivering their work, but their responsibility for making sure it stays working and it works in its intended application doesn't end when they're done with the job. In other words, they're on call for the rest of their lives. I know, not that bad, but for a reasonable amount of time. And so I want that accountability to follow through, and people feel that accountability and be expected. So these are examples of safety nets we have at JPL. Do we have, so are you given personal space to feel? Do you have time to think and mull? Do you let people say stupid things, or your team members let you say stupid things in meetings without putting you in your place? When you fail, you're given a second chance to try again and encouraged to learn from your mistakes. Does your boss or you allow lessons to be shared with others outside your circle without worry that shortcomings might be uncovered by someone else? I gave a similar talk like this to our HR department, and I explained to them that I had personally destroyed flight hardware in no less than 3 different flight Mars missions. And they looked at me like, I see a common mode fault here. I can't believe you're still. I haven't been fired once. And they said, maybe you should have been fired. Well, that could be true, but that might be. But there are 3 independent different situations that all were things that were lessons that I share with other people, and I'm not ashamed to tell people about my mistakes and our mistakes together, because it's really that's how we learn. That's how we get better as a community and as a species. Anyway, so I think we have to balance authentic confidence with attempting hard things with humility, balancing humility and hubris. The taxpayer obviously expects us to be good, so we have to be somewhat bold, but we can never leak into hubris. If we don't acknowledge people who do not acknowledge the fallibility are doomed, and we are fallible. It's so easy to when you see something work to sort of like pat yourself in the back, but it may not be that close to failure. Something else is important. Everyone, I mentioned this earlier. Everyone knows something you don't, regardless of their education. There's always somebody smarter than you at all times, no matter who they are. The janitor doesn't matter. They know something you don't. You should treat them that way, and they should, and likewise. We need to listen to the quiet voices, the people who don't say much. There are certain organizations, certain groups of people. I won't mention software people, but there's certainly people who are not software developers who are not outgoing and who don't step up and pound the table when something goes wrong. They sit silently but that's okay. The team leads have to be active listeners, and they have to go out and ask and inquire and let the quiet people speak. Everyone has something you can learn from, and we should treat them that way. And we only succeed if we count on each other. So I think failure enables our growth. So talk about your failures, talk about your mistakes. It actually is a great way of getting friends. People will trust you more when you're honest about your own fallibilities. And then make your failures productive. share them. Encourage a culture that welcomes openness. Humility, respect, and teamwork are at the root of all of our successes. And failure, much of that, many of our failures are examples where we don't do that. And so sometimes things work out. So I'm just going to end here. But if you have any questions, I don't know if I leave myself a lot of time for questions, but I'm more than willing to answer questions in the short time we have left. Yeah, thank you. Thanks. So any questions?
Yeah, let's take some questions. We have plenty of time. So don't be shy. Come on up.
Yeah. Any cool failures that you want to share, or examples where we didn't share? We probably should have shared.
Oh, there's not enough time.
Not enough time.
So seeing something, we were talking about the wheels.
Oh
And the
yeah.
fact that you convinced yourself, you saw the test data, but you convinced yourself it was A rather than B.
Right.
I mean, if anything keeps me up at night, it's that.
Yeah.
So was there something in the slides that you would say that you wish you'd learned or wish you had done back then?
Great question. Is there something? I think even at the time there's a little voice in the back of my head saying that we were being hasty, and because we were really running out of time. We were so busy. We came to this conclusion. We had a couple meetings on the topic, went through the data, and said, okay, this is not a problem. Okay, when things go funny, I mean, even when you have a test and you realize that you did an over test, or you pushed it to the limit, or you're operating outside its normal specification and it doesn't work, I think those are very important hints about how the system might not work when you think it does.
Or the test ran 1,000 times, but one time it failed.
Yes, it runs
1,000. It failed 999 times. I mean, it
That's
passed
right.
199 times.
I think, Outriders to me are the most insightful pieces. Granted, you don't want to spend vast sums of money, taxpayers' money, looking at trying to explain a problem because you overtested something. But on the other hand, you should really spend a little time understanding why it took you off the road and why it broke, because especially if it violated your expectations. Even though you might, we didn't design it for that condition, we said. Well, but why did it break? Should it have broken in these situations? I know it's beyond their spec, but maybe it really ought to work. Should have worked. And we all had that in the back of our mind that it probably should have worked, but we didn't think it through. And I feel very guilty about that.
Thanks for the talk.
Thank you. Yeah.
Hi. You mentioned that one of the root causes of the Mars Climate Orbiter failure was people not being willing to speak up. And
yeah.
And we had the Psyche IRB report come out last year at JPL, and we heard the same thing 20 years later. How can we at JPL and the industry as a whole solve this problem, make it possible to speak up?
That's a great question. And I'm finding it, to be honest with you, I'm not sure how. I think it really starts with management. You have to create a very relaxed, comfortable atmosphere. When things go wrong, do not blame the messenger. You've got to be almost overboard in encouraging people to say what they really think, and actively get them comfortable. I mean, for teams to be successful, all of you have been in teams that have been super successful and you can tell when you're in a successful team. Why? Because your team members can finish your sentences. They seem to think like you think. Now, that wasn't because they were brought in because of that. Hopefully, they morph into a single mind, a hive mind, of people who actually are in this term, esprit de corps, where people are really on the same page. They're comfortable in their own skin and they're comfortable in the skin of the group, right? And I think that's a very important humanistic feature that needs to be somehow developed. And as engineers, we're not really trained to do that. We're not, and none of us are. We like technical stuff. We're not good sociologists. And so to be honest with you, I don't know how to fix that. I know the Jet Propulsion Laboratory right now is having conversations as we speak right now in Building 180 about this very topic. How do you encourage people to feel comfortable and not feel threatened or feel like an out, especially if there's a sense of you're pointing at somebody or some subgroup to being a problem because it feels divisive when in fact it doesn't have to be. So I don't know, but I think it's one of the most important features of success is a team that is comfortable to speak up, and organizations and are not, do not diminish others who do so.
Thank you.
Hi.
Hi, Rob. I'm Alexandra Holloway. I'm the 7th or 8th flight software lead on MSL, and you are cordially invited to. I have a question. This is a question. You're cordially invited to the flight software review for the R13 flight software, which is about to get installed on the vehicle.
Oh my gosh, 13. Wow.
So, how you as a reviewer who is kind of maybe you haven't been keeping up with the hot topics in flight software on MSL. How do you review? How do you attend a review where you're not necessarily the expert?
I'm useless this way. I mean, I obviously I can't. I mean, I do have some ancient memory of how software is supposed to work because I used to do that myself as part of my career. But I've got to defer to experts. But I use the very thing we're just talking about. When I go to a group meeting, the thing that I assess. That's why WebEx has been a mixed blessing. We all do collaborative work together, but oftentimes I want to see the body language. I want to see how comfortable people are. I want to see the dynamics of the team themselves. I want to see how people are. How do they feel about the work? How do they feel about what they're nervous about? I want to be able to see that. And I actually I'm assessing it often from a sociological perspective. Because again, I associate positive team inter-team dynamics and curiosity and questioning with success, and when I see that, I'm happy. And so I see people who show their desire to be technically authentic and are confident, and their team shares their confidence. I don't have to find out for real what they're doing. I will trust them. And I think that's an important feature that's what I do to evaluate teams and how they work. When you get down to whether you want a hard coded value or do you want to put it on in the parms on the flash, that's your call. But I think there's a lot. But it's that at higher level that I evaluate at this level, especially since I can't claim a technical authenticity anymore.
All right, we have time for one last question. Okay.
All right.
Thanks.
Maybe this is a little broad one, but how do you balance the failure and iteration cycle at a high level, program level? Ranger launching every 2 months,
right.
Launch vehicles versus Mars every year or every 10 years?
That's a great question. Well, to me, it's a huge battle to balance that because what I see happening, at least within the programs that I'm witness to inside NASA, is a shortening of the time when that kind of iteration is key to success. Particularly in the hardware development world, they've taken the time between PDR and CDR down to less than a year. And how can you develop? I mean, the amount of work you need to do to get to a final design is hard. And you're flying the first thing that came to your mind. It's the first instant. There's no time to refactor, to rethink it through. And while software has a little more advantage to keep iterating on that, almost always the software has to be there to patch up the mistakes that the hardware architecture has provided, or we've done such a poor job of functional decomposition for programmatic reasons, oftentimes, where it's the architecture just doesn't make sense for the most cost-effective and simple design. So I've seen that time being truncated. And so people like me will argue, like, listen, give these people time. Make sure they have a test venue to test their work. There was a time that we had key soft sim environments that were developing that developers were working on to check that their design worked, that had a lot of the hardware models built in, but it was not funded as a legitimate verification venue. MSL started that way. Remember, we didn't have WISTAs. It was considered an afterthought. And we had, because of money crunches, they were cutting down the number of test venues. So there are less test beds. We're less hardware rich. And it's particularly so much of our software is coupled to the system being built. So I evaluate it on a case-by-case basis, but I'm constantly feeling frustrated that it's not enough time for people to talk, not enough time to even the team. You think about what phase A is. We talk these phase A, B, C, D. What is the purpose of phase A? Phase A is for the team to get to know each other and roughly agree what they're going to do. That's the whole purpose of phase A. So you really haven't done anything. You've made some PowerPoint packages. Phase B, you're starting to get real. You're starting to think about how it's really going to do. By the time you get to phase C, you're supposed to have we're working toward a flight design and detail design. But then that's when you discover all those decisions you made a year and a half ago were mistakes. And so what about the time to fix it? Well, there isn't any time. And so I find it very frustrating. But I think all of us should keep our eyes out, ask ourselves, how are we going to see this through? Just don't think about the thing that you want to build, but think about its whole life cycle, how it's going to get there, and in the context in which it gets there. You've got to visualize all those things. And I think, and you have to fight for them, because a lot of managers will deny you the resources to be able to check your own work. And I think we have to fight.
Thanks.
Thank you all very much. Appreciate it. Great review.
All right.